Suppose I tell you that I have a series of 4 numbers. Without any more information, you're free to imagine absolutely any 4 numbers. And we say that the degrees of freedom in this case is 4. Now imagine that I also tell you that the mean of these 4 numbers is 6. Now a constraint has been added, which means that you can't imagine absolutely any 4 numbers anymore. I can pull out 1, 2, 3 numbers out of a hat, but once I have reached 3 numbers, the 4th one has to be a particular number such that the overall mean is what I told you. Let's try this out. I can choose anything for the first number, say 5. Then I can choose anything for the second number, say 4. Then I can choose anything for the third number, say 8. Now once we have chosen 3 of the 4 numbers, the 4th number can be only one thing if the mean of the series is set at 6. The 4th number has to be 7. No other number in the 4th place would give a mean of 6. So I had the freedom to choose any 3 numbers, but once those 3 numbers were chosen, the 4th was fixed. We say in this situation that the degrees of freedom is n-1. In general, the degrees of freedom to be used in a calculation is the total number of data points minus the number of parameters previously estimated from the data. In this example, we have calculated one parameter, the mean, so the degrees of freedom is 4 minus 3. In fact, in many statistical applications, it's more appropriate to use the degrees of freedom rather than the overall sample size. So with that in mind, let's get back to our measure of variation. We divide by the degrees of freedom rather than the sample size, and so now this quantity is the average square deviation from the mean. This is a standard statistical measure called variance. And since the numerator has squared deviations, the variance is in square units. If x is centimeters or peacock's tail, then the mean may be 130 centimeters, but the variance is, say, 25 centimeters squared. To bring the variance back to the original units, we have to take the square root, so 5 centimeters. And this is called the standard deviation. Recall also that these calculations are being performed on a sample from the population we want to generalize to. So what we have is the sample standard deviation S, which you hope is not very far from the population standard deviation sigma. Again, Latin letter for the sample estimate and Greek letter for the population parameter. Variance sometimes is not given its own symbol, but rather is represented as S squared or sigma squared, depending on whether we mean the sample variance or the population variance. Now, intuitively, you can think of the standard deviation as the average distance of data points from the mean. But in actual fact, it's a bit larger than the average distance because squaring the distances before averaging gives extra weightage to more extreme data points, something that's generally worth remembering. By the way, you might also see a formula for standard deviation that has n in the denominator rather than n-1. And the difference is this: if you have the full population that you're interested in, then you would use n. If you have a sample from the population, then using the degrees of freedom n-1 is what is used. In nearly all research, we are sampling from a larger population, and so we use the degrees of freedom rather than n. Now, one point that people often get confused about is what happens to the standard deviation when sample size increases. Let's look at this by first examining what happens to the mean. Let's say we have a series of numbers, which is our sample from the population. We start with the first number in our sample and then the second and the third. And as we proceed with our sampling, we go from left to right in this graph, adding numbers and calculating the running mean with each additional data point. As you can see, the mean bounces around at low sample sizes and then gradually settles down, converging on what we hope eventually is the true population mean. The running standard deviation of the same sample shows a similar pattern, fluctuating at first and then settling down near what we hope is the true population standard deviation. Now, some people look at the n in the denominator of the formula for standard deviation and therefore expect the standard deviation to decrease with sample size. But that doesn't happen because for each additional sample, each additional n, an additional deviation is being added in the numerator as well. So this far we've talked about how to describe our data in terms of different measures of central tendency and variation. But in the context of research design and analysis, our goal is most often to be able to say something about the unknown population parameter from our sample estimate. Let's explore that next. Say our research task is to find out the density of peafowl in Tadoba Sanctuary, or to measure the mass of 10-day-old bustard chicks, or to say something about the proportion of time that male quails spend singing in the breeding season. For all these, we take some sort of sample, whether of transects or of broods or of individual birds, and from the mean of these samples, we want to say something about the population. In other words, we hope to get close to the population parameter, in this case the mean, through our sample estimate. So we go out, follow all principles of good study design as discussed in the previous video, and come up with some estimate of the population mean. Now, how do we know the precision of this estimate, or its inverse, the uncertainty in the estimate? The precision or uncertainty is a crucial component of our result, so that we can conclude something about the population parameter. Our best guess for the parameter is, of course, the sample mean, but the question is it a good guess, a precise guess, or is it a poor guess, an imprecise guess? We do this by constructing what's called a confidence interval, a range within which the true population mean is likely to fall. So we might say that our best guess or estimate for the population mean body mass is 18.5 grams, and we're fairly sure it's somewhere between 16.5 and 20.5 grams if our guess is somewhat precise. Or we might calculate that it's somewhere between 14.5 and 22.5 grams if our guess is not so precise. So how do we calculate the confidence intervals? How do we calculate the degree of precision in our guess? We begin by recognizing that when we take a sample of, say, 30 data points from a population, this is only one of many possible samples of 30 we could have got by chance. We just happen to choose these specific 30 sampling units from which we measure these 30 numbers and calculated a mean. If we had run our random number generator again and sampled another 30, we could have chosen a different set with potentially different measurements and a different mean. And here's another set of 30 numbers we could have sampled, again with a different mean, all differing by chance. So the 30 numbers we happen to measure are one set out of potentially thousands or millions of possible sets we might have drawn by chance. One aspect of major interest is to ask ourselves, if I had drawn another set of 30 from the population, or another, how different would these have been from the actual set of 30 that I did get? If all sets give very similar sample means, that means that chance had a relatively small effect here, and no matter what set of 30 I happen to get, the sample mean is likely to be close to the population mean. On the other hand, if the possible sampling sets are very different in their means, then chance looks to have a very large role to play, and some sample means could be quite far from the true population mean, and perhaps the sample mean that I got in my data is in fact quite far from the true population mean. Now, if only we could construct a frequency distribution of sample means from lots of possible sets that we could have drawn from the population. If we had such a frequency distribution, we could see whether it's a tight distribution with very little variation or a broad distribution with lots of variation. In the first case, we will have more confidence that the population mean is close to the sample mean that we got than the confidence we will have in the second case, where it's a broad distribution of sample means. Now, we won't be able to actually sample the population many times to create this frequency distribution, but we can do the next best thing. We take our sample data set as our best representation of what the population is like. It's really our only representation of what the population is like. So, imagining that these numbers look like the population as a whole, we convert this sample into an imaginary population by repeating the numbers many times. And then we draw a random set of numbers with the same sample size as the original from that imaginary population. and we calculate the mean of that sample. And we repeat this, drawing repeatedly a sample of size n, our original sample size, from the imaginary population, each time calculating the sample mean and writing it down. By the way, in practice, this is called sampling with replacement. It's the same if you write down your n numbers on small pieces of paper, which you all put in a single basket. And then for the first sample, you randomly choose one paper, note the number written down, put it back, choose another paper, note the number down, put it back, and so on until you have n numbers. So that's sampling with replacement using pieces of paper in a basket. So this method of sampling with replacement from a set of numbers is called bootstrap. And you carry out this bootstrap procedure many times, each time calculating the mean of the bootstrap sample. Let's say you do this 1,000 times. Then you can draw up a frequency distribution of the 1,000 bootstrap means. When compared with the original distribution of the raw data, the distribution of bootstrap means is much narrower, which makes sense since although the data might be widely distributed, the distribution of means will be narrower because the mean is after all a measure of central tendency. And as the sample size of the original sample increases, the distribution of bootstrap means becomes narrower and narrower. So how does this distribution of bootstrap means help us in determining the precision of our original estimate? That is, how closely the sample mean is likely to be to the population mean. Well, it depends on the width of the distribution of bootstrap means. So then how can we characterize the width of this distribution? We can do so exactly the way we did so before, when we were talking about the distribution of the raw data rather than the distribution of bootstrap means. We can calculate the root average square deviation from the mean, otherwise known as the standard deviation. In this case, the overall mean is the mean of bootstrap means, and we are looking at the deviation of each bootstrap mean from the mean of bootstrap means. Remember that the bootstrap means represent different possible outcomes we could have got if we had sampled another random set of data. And the bootstrap frequency distribution represents the range of those possible outcomes. Now, I apologize, but it's time to introduce another bit of jargon. While the standard deviation of a set of numbers is simply called the standard deviation of the means we spoke about is called the standard error. Don't get thrown by the use of the word error here. In this statistical context, the word error means deviation or difference. It does not mean mistake. So how do we interpret the standard error? The standard error is a measure of the precision in your original sample estimate of the unknown population mean. A large standard error tells you that the distribution of bootstrap means is large or broad, and therefore your precision is low. The true mean could be anywhere within a large range of values. By contrast, a small standard error tells you that the distribution of bootstrap means is small or tight, and therefore your precision is high. The true mean is likely to lie between a small range of values. But say that's not good enough. We want to be able to describe an actual range of values between which we think, based on the data, that the true population mean lies. For example, we want to say that our best guess is the population mean lies between 12 and 14 or 11 and 15. How can we get those numbers? Well, one way to do this is to go back to the distribution of bootstrap means. And now we take advantage of what we've learned about percentiles and quantiles. We could ask what value corresponds to the 5th percentile or the 0.05 quantile, and what value corresponds to the 95th percentile or the 0.95 quantile. If you're following carefully, you will realize that 90% of the distribution lies between the 5th and the 95th percentile. If you haven't understood this, it might be good to go back and review the section on quantiles. So we call these two values the confidence limits and the range between them the confidence interval. What we have done now is to identify the 90% confidence interval within which 90% of the bootstrap means lie. More conventionally, you look up the 2.5th percentile and the 97.5th percentile, and through that identify the 95% confidence interval within which 95% of the bootstrap means lie. Some people advocate using the 50% confidence interval instead. And of course, the nature of frequency distributions and quantiles is such that the 50% confidence interval is narrower than the 90% confidence interval, which in turn is a bit narrower than the 95% confidence interval. Now, how does the confidence interval help us and what does it mean? The confidence interval represents a range of values in which the unknown population mean is likely to fall. Formally speaking, if we collect a sample of data and construct a 95% confidence interval as just described, and do this repeatedly, each time constructing a 95% confidence interval, then the true population mean will fall within those intervals in 95% of cases and will fall outside those intervals in 5% of cases. In the simulation shown here, the true population mean is 12, and you can see that in 3 out of 50 confidence intervals marked with red arrows, the mean, which is 12, is not included in those 3 confidence intervals. So in 47 out of 50 confidence intervals, on 94% of cases, the confidence intervals contain the true mean. Similarly, if we construct a 50% confidence interval for a sample of data and go out and do this again and again, each time constructing a 50% confidence interval, then the true population mean will fall within those intervals in 50% of cases and will fall outside those intervals in 50% of cases. So to summarize, your 95% confidence interval will contain the true mean in 95% of cases. Your 50% confidence interval will contain the true mean in 50% of cases, and so on. And this is, of course, assuming that your sample is unbiased and randomly chosen from the population and all that good stuff. Statistical analysis can't make up for flaws in study design, unfortunately. So now to recap, we have calculated a measure of central tendency, say the mean, and we have a measure of precision, the confidence interval. The narrower the confidence interval, the greater the precision. That's all we need in order to say something about our measurement of a single quantity. But here's a question. When constructing confidence intervals, is there a shortcut we can take rather than going through all this fuss about sampling and resampling and calculating all those bootstrap means and so on? Well, yes, it turns out that there is a shortcut. And in fact, it's something that was used almost exclusively until personal computers became widely available and is still often used today. It turns out that under some circumstances, we don't need to do the bootstrap process to get a distribution of bootstrap means and then take the standard deviation of bootstrap means in order to calculate the standard error. Instead, we can use this simple formula to calculate the standard error. Note that because of the extra n in the denominator, the standard error does get smaller as n gets larger, unlike the standard deviation, which may fluctuate but does not decrease as more samples are added. Okay, now we have the standard error. How do we get to the quantiles? It turns out that under some specific conditions, the standard error has magical and very useful properties. For example, in a particular kind of frequency distribution of means, the standard error has the property that if you take the mean of the means and look at the range encompassed by the mean plus or minus 1.65 times the standard error, then that range covers 90% of the distribution. Or if you look at the range encompassed by the mean plus minus 1.96 times the standard error, then that range covers 95% of the distribution. Now, where does 1.65 and 1.96 come from? Where do these multipliers come from? They come from the properties of a particular specific distribution called the normal distribution. And it's only for a normal distribution that these properties hold. The normal distribution is a symmetrical distribution characterized by two quantities, the mean in the middle and the standard deviation. What you see here is a histogram, but one can also draw a distribution as a line rather than in steps. Roughly speaking, the height of the line for any x value represents how common that value is in the distribution. For a normal distribution, the mean lies at the middle, which is also the highest point on the curve. Changing the mean shifts the curve left or right. The standard deviation specifies how wide the curve is. The smaller the standard deviation, the narrower the curve, with extreme observations being less frequent. And the larger the standard deviation, the broader the distribution, and extreme observations are more frequent. You'll need to be alert if you don't want to get confused. Remember that we use the term standard deviation to refer to the root average square deviation of raw data, and standard error to refer to the root average square deviation of means. But the term standard deviation is a generic term for any distribution, and you will have to be alert to know when it is the variation in raw numbers being talked about, or when it is the variation in means being talked about. So for any particular value of mean and standard deviation, the normal distribution has a fixed shape. Here is the normal distribution with a mean of 20 and a standard deviation of 5. With this information, we can find out what proportion of the distribution is covered within any particular range of x. In fact, it's most convenient to measure the distance from the mean in terms of not x, but standard deviations of x. So we can do a small transformation. Subtract each data point from the mean and divide by the standard deviation. The resulting numbers have a mean of 0, because now positive and negative x's balance out, and a standard deviation of 1. This new distribution is called the Z distribution, or standard normal distribution, and we have converted the original data into what is called Z scores. The Z scores are the deviations of the data point from the mean, but measured in units of standard deviation. So in the original normal distribution, if a data point has a value of 10 and we know that the standard deviation is 5, that means that 10 lies 2 standard deviations below the mean, and therefore it has a Z score of -2 and is placed at -2 in the Z distribution. Conversely, if the Z score is 1, then we know that the data point lies 1 standard deviation above the mean, and we can calculate, knowing the mean and standard deviation, we can calculate that this is at a value of 25 on the original scale of the data. So you can convert between the original data and the Z scores in either direction. Finally, from the properties of the Z distribution, we know that the range -1.65 to +1.65 covers the central 90% of the distribution. This corresponds to ±1.65 standard deviations from the mean in the original data, which is ±1.65 times 5, which is ±8.25. So in the original distribution, 90% of the data lie between 11.75 and 28.25. Similarly, in the Z distribution, the range -1.96 to +1.96 covers the central 95% of the distribution, which corresponds to 10.2 to 29.8 in the original data. Please work it out for yourself and see if you get the same numbers that I did. So now we can take full advantage of the normal and the Z distributions. If we have our sample mean and sample standard deviation, we can calculate the standard error. And then we know from the properties of these distributions that the mean ±1.96 times the standard error contains 95% of the distribution of possible means we could have got had we sampled repeatedly. And so the 95% confidence interval is mean ±1.96 times the standard error. And if we wanted a different coverage, say of 90% or 50% for the confidence intervals, we would just need to look up a Z table to see what the multiplying factor would be. Please carefully understand once again the difference between standard deviation and standard error. Standard deviation describes the variation in the actual data points. The mean ±1.96 times the standard deviation would encompass 95% of data points if the data follows a normal distribution. On the other hand, the mean ±1.96 standard error would encompass 95% of the imaginary means from imaginary multiple sets of samples. In other words, standard deviation describes variation in the data and standard error describes variation in the means. You use standard deviation when you want to describe how variable your data are. You use standard error when you want to describe how precise or the converse, how uncertain your sample estimate of the population mean is. Now, as discussed in the earlier lecture on research design, the uncertainty of your sampling estimate is directly proportional to the variation in the population and inversely proportional to the sample size. More variation in the population leads to more variation in your sample, which is reflected in the standard deviation of the sample. Higher sample size brings the means of multiple separate samples close together, reducing the standard error. And this is also reflected in n being in the denominator in the formula for standard error. Now, I said earlier that the standard error has these magical properties under certain conditions. The specific condition is that the distribution of sampling means, of which our observed mean is 1, follows the normal distribution. If it doesn't follow the normal distribution, then we can't use the multipliers 1.96 and 1.65 and so on. And life gets more complicated. Now, we often see that people just assume that the conditions of a normal distribution apply. So the question is, how reasonable is this assumption? Well, it turns out that under a surprisingly broad range of conditions, it is a fairly reasonable assumption. We find that even if the underlying data look very different from a normal distribution, the distribution of means from multiple sets of samples from the same data looks quite symmetrical and normal. In fact, this observation is codified in what is called the central limit theorem, which says that the distribution of sample means approximates a normal distribution as sample size gets larger, and especially if the underlying distribution is not too asymmetrical. Here are some examples. Here we have a distribution of the underlying data that is very different from normal, something like a uniform distribution, and the most common values aren't even at the center. But when you take repeated samples from these exact data and plot the distribution of means, you see that the distribution of means is quite symmetrical and almost like a normal distribution. The most common value of the mean is towards the center, and that's because the act of taking the mean tends to shrink values from the extremes of the distribution towards the center. It's worth pondering about this a little bit to see if this makes sense to you. Now, this distribution is what you get when you take samples of size 6 at a time. So your sample size is 6, and repeat this over and over, calculating the mean each time. If you were to take larger samples of size 30 instead, then the distribution of sample means would look even more like a normal distribution and would also be narrower. I hope by now you understand why. If we started with a very different shape distribution of the data, this one is skewed towards the right with a small number of extremely large values. Then if we drew samples of size 6, the distribution of resultant means looks a bit more symmetrical, but it's still skewed somewhat to the right, so not quite symmetrical. But if we took samples of size 30 each, then the distribution of resultant means is very close to normal. So these two examples demonstrate the central limit theorem, which holds that the distribution of means is approximately normal, especially when the underlying distribution is not too skewed and when the sample size is large. So in many cases when we are dealing with numeric data, it can be reasonable to assume that the distribution of possible sampling means is normal, and we can then use the properties of the normal distribution to calculate the precision of our estimates. But beware of variables that have lower or upper limits like 0 or 1. For these, the assumption may not hold, particularly at small sample size. And one further point, if your sample size is less than 30, the distribution of means is likely to be a bit different from a standard normal distribution. In this situation, the distribution is likely to follow what's called a T distribution, which is like a normal distribution, but with a higher frequency of extreme values. In other words, with greater area under the two tails, the extreme values to the left and right of the mean. So when the sample size is less than 30, one must use a multiplier from the T distribution, not from the standard normal distribution. You know that for 95% coverage in the normal distribution, you have to look at plus minus 1.96 standard deviations from the mean. And this multiplier doesn't change with sample size. By contrast, the T distribution changes shape as sample size increases, and so the appropriate multiplier changes as well. As the sample size gets larger and larger, the T distribution shrinks towards the normal distribution. For example, for a sample size of 4, usually corresponding to a degrees of freedom 3, the multiplier is as high as 3.18. But as the sample size increases, the t distribution shrinks towards the normal distribution and our multiplier gets closer and closer to 1.96. So because the t distribution reduces to the normal distribution at large sample sizes, in practice most statistical software programs always use the t distribution to calculate the multiplier, since it takes care of matters regardless of sample size. So that brings us to the end of our description of what is involved in measuring a single quantity. We are typically interested in some measure of central tendency, most often the mean, but given the mean's lack of robustness, perhaps we should use the median more often. Also, if you want to understand the variation in our sample, then we can visualize it using a strip chart or a histogram. Note in the strip chart the points are jittered, that is, each point is moved a small distance at random along the vertical axis so that points with exactly the same values are visible and don't obscure each other. We can summarize the variation by calculating the interquartile range or the standard deviation, or for that matter the 2.5th and 97.5th percentiles, and we can overlay these on the graph. Now this is for describing the variation in the sample. If on the other hand we are trying to make inferences about the population parameter like the population mean, therefore we need a measure of precision of the estimate from our sample, and we would calculate something like the 95% confidence interval around the sampling mean using a bootstrap method, or if it's justified, we can take the shortcut of calculating the standard error and use the properties of the normal distribution to find out the limits of the 95% confidence interval. And if this is of primary interest to us, then we would show the confidence interval in the strip chart or histogram rather than the standard deviation. When you're making graphs like this, please ensure that you label your graphs carefully to tell the viewer what measure of central tendency you're presenting, whether it's mean or median, and which measure of variation you are showing, the standard deviation or interquartile range, for example. Or if you're presenting precision, then are you showing the standard error or the confidence interval? And if you're showing the confidence interval, then what percent cover of what is it, a 90% confidence interval or a 95% confidence interval, and so on. While estimating a population parameter like the mean, remember also that if the confidence interval is very large, then we may actually have learned nothing much from our study. So it's useful to work backwards in specifying what degree of precision you're aiming for and then calculating what sample size you might need given the variation in the population. For example, let's say I want to estimate mean p-foul train length with such precision that I get a 95% confidence interval that spans a range of only 4 centimeters. So what we need is for 1.96 times the standard error of our study to be around 2 centimeters, since we calculate the mean plus as well as minus that number. And that will give us an overall confidence range of 4 centimeters. So we require a standard error of roughly 1. Now if I do a small pilot project measuring the train lengths of 10 p-foul, and the mean of these 10 is I find to be 125 centimeters with a standard deviation of 8. Then assuming that this sample standard deviation of 8 is somewhat close to the population standard deviation, I know that the standard deviation divided by the square root of n will be my standard error, which we know needs to be around 1. So therefore the square root of n needs to be around 8, which means that the sample size in my final data collection should be roughly 64 individual peacocks. By contrast, if I were fine with a 95% confidence interval spanning a range of 8 centimeters, then my sample size would only need to be around 16. So now you know the answer to that eternal question, what sample size should I have? The answer is that it depends. Specifically, it depends on the variation in your population, and it depends on how much precision you need in order to address the research question you are tackling. The first you can measure in a pilot study or possibly by getting a clue from the literature. The second is a decision you have to make, often a subjective decision, and a decision you still have to make even if you're uncomfortable with the subjectiveness of it.